For Chapter 3, we're going to discuss probability of discrete random variables. First, let's start with some definitions. Probability is really the measurement that's associated with how certain we are of a specific outcome when we're doing a particular experiment or activity. An experiment is a planned operation that we carry out under controlled conditions. And experiments will result in something called observations or outcomes. Most of the time we will call these observations. When we talk about the sample space of an experiment, that's really the set of all possible outcomes, all possibilities. When outcomes are equally likely, that means that each outcome of an experiment occurs with equal probability. Now, you're very familiar with this. When you toss a coin, you have equally likely outcomes. You're just as likely to get heads as you are to get tails. There's a 50-50 probability with either one. So what we do to represent this is we draw something called a tree diagram. I realize this doesn't look like a tree. It's sort of like a sideways tree. But we start off with one toss of the coin. And now our first toss of the coin results in either heads or tails. Then we toss the coin another time. The second one also results in either heads or tails. But it's also the outcome, the final outcome of our two tosses of the coins is contingent on the outcome of each toss. So we could have gotten heads on the first toss and heads on the second toss. Our outcome for those two tosses would be heads, heads. We could have gotten a heads and then a tail on the second toss. That would have given us an outcome of heads, tails. Same thing happens if we start and the first toss is tails. Well, then we get an outcome of tails, heads, or either tails, tails. So with two tosses of the coin, two possibilities for each toss, we have the possibility of 4 different outcomes. Let's take this discussion of tossing the coin just a little bit farther. Let's talk about 3 students from IRSC. In other words, we've got 3 selections, 3 students, and we're going to select these students and then we will make an observation. Our observation is going to be whether they are enrolled full-time or part-time. And we want to draw a tree diagram for the selection of our 3 students. First, my first student, I'm going to just draw the first opening here, and I'll put up here that this is student 1. And for student 1, I can have either a part-time student or I could have a full-time student, and I'll represent them just with part-time, full-time there. So that's my first selection. The second selection is going to give me the same possibilities. It will either be a part-time student or full-time. And if the first one was full-time, my second one could have been either part-time or full-time. Now, my third one is going to come and build on still the second selection of students. And of course, it's either part-time or full-time for each one. Now, this was really, and I'll just draw some dots so you can see what I'm doing here. This was really student 1, and here is my second selection. This would be student 2 that I selected, and over here is student 3. Now, what are the all possible outcomes for this selection of these students? Well, it could have been part-time, part-time, part-time. Now, I'm going to represent that with just the first letter. So I'll say the first possibility is 3 P's. The second possibility will follow this chain, part-time, part-time, and full-time. Next, we've got to go down here. We're going to say part-time, full-time, part-time. So I've got P, F, P. And then the next one, the fourth one is part-time, full-time, full-time, P, F, F. Next, I finally get down here to my first selection was a full-time student, so full-time, part-time, part-time is F, P, and P. And then full-time, part-time, full-time is going to be F, P, and F. Then I have full-time, full-time, part-time, FFP, and finally, the last one is all full-time students were selected. This is all possibilities for selecting 3 students when they have only 2 possibilities for each selection. Now, as you can imagine, we're going to have quite a bit of discussion about the combination of these different outcomes, and we will look at these combinations of outcomes and call them an event. An event is usually represented by uppercase letters like A and B. And an example would be if an experiment is to flip a coin, event A might be getting at most 1 heads. So the probability of that happening would be written probability of A, P of A, and that's how we're going to write it. Now, you could write that A is at most 1 head, and so you could write probability of at most 1 head. It's usually easier to define the event as a capital letter and then just write probability of A. Now, a simple event includes only 1 possible outcome, and a compound event means that there is more than one possible outcome included in our event. Let's start talking about events by looking back at the tree diagram that you drew on the previous page. These are our 3 students, and these are the possible outcomes, and I've listed them here for you. And the event that we're interested in is the event that at most 1 student is enrolled full-time. Now, I've done this one deliberately because this is the most confusing wording that you will see in your looking at probabilities when they ask you at most 1. So you have to think, okay, so 1 full-time student would satisfy the condition, but you also have to consider that no full-time students, 0, would satisfy the condition also, and that's the one that trips us up. At most 1 means that it could be either 1 or 0 full-time. So we go over here to our far right and we look at the possible outcomes that we had, and we see that we had part-time, 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 at most 1 full-time. This meets the criteria because it's 0 full-time. So that one I've underlined and italicized. And the next one I look at is part-time, part-time, full-time. Well, there is at most 1 full-time. There's 1 full-time, so it meets the criteria. Then I've got part-time, full-time, part-time. I've still got 1 full-time, at most 1 full-time. This one meets the criteria. The 4th one has 2 full-times. That's over the limit, so it doesn't help me. But full-time, part-time, part-time does, at most 1. Now the rest of them have more than 1 full-time, so they're out. But I managed to get 1, 2, 3, 4 of my different possibilities here could have been satisfying the condition or the event at most 1 full-time. So I would look at event A as being at most 1 full-time, probability of at most 1 full-time. 4 out of the 8 met that criteria. 4 out of 8, of course, is 1/2, 0.5, or I could say that's 50%. So how would we talk about this? Well, we'd say there's a 50% probability that at most 1 student out of the 3 is enrolled full-time. I want you to get some more definitions. So really these are rules about probability, and we call them the properties of probability, 2 very important properties, and you'll have to remember these for the rest of your time here in this course, so be sure you make a note of them. The probability of an event always lies in the range of 0 to 1. There's nothing, it could be that there's a probability of 0, it could be that there's a probability of 1, or anything in between. It will never be negative, it will never be greater than 1. And the sum of all of the probabilities of any simple event, and this is all the final outcomes, the sum of all those final outcomes, if we look at their probabilities, is always equal to 1. Now, this makes sense when you think of the probability that an event cannot occur, an event that, or I'm sorry, let me reword that. An event that cannot occur, it's an impossible event, would have a 0 probability. Now that's called an impossible or a null event, and you might want to make a note of that since I didn't put that on your guided notes pages. An impossible or null event has a probability of 0. It cannot occur. Now, an event that is certain to occur, that always occurs, has a probability of 1. We call that a sure or a certain event. Now let's do this exercise just to see if you understand those two probabilities or what we were talking about. First, I want you to circle any of the values that cannot be the probability of an event, and be sure you can explain why. Stop your tape for just a second, get that done, and then come back. So let's look at the first one, 2.4. Well, it's definitely over the number 1. So this is out. It cannot be the probability of an event. Now 3/8 is a fraction. 3 over 8 means that's smaller than the number 1, so it's okay. But a negative number, the third one, cannot be. No negatives are included. 0.55, definitely between 0 and 1. It's okay. 9/4 is over the number 1, so it's not okay. Negatives are out again. -2/9 would not be okay. But a probability of 1 is fine. A probability of 0 would also be fine. And 12/17 is definitely a good probability. The next thing I want to talk about are conceptual approaches to probability, and we're going to discuss 3 of them. We're going to talk about the classical probability, and then relative frequency probability, and then the third one, subjective probability. Now, one of these you're going to use quite a bit, and one of them you're not going to use at all, but they're still important that you know the definitions. The first approach we'll talk about is called classical probability. Now, classical probability is a simple form. It has an equal chance of occurrence. The odds are equal that each of the outcomes would occur. So now, what happens is we call these equally likely outcomes. In this approach, we have to know all of the possible outcomes. So that makes them actual or something called theoretical probabilities. One example of classical probability is one we've already discussed, and it's tossing a coin. You know the actual probability or the actual or theoretical probability of tossing a coin. The probability of heads is 0.5 or 1/2. The probability of tails is also 1/2. So those are equally likely outcomes, and they meet our criteria for being classical probability. Now let's talk about tossing a die. Now a die has 6 sides, and it has 3 even sides, and 3 of the numbers are odd. So what would be the probability of an even number occurring when you toss a coin? Well, it would be 3 out of 6. We could reduce that to 1/2 also. So the probabilities of an even one and an odd is also equally likely outcomes, and this is another example of classical probability. The next probability, what we call relative frequency probability, is the one that we're going to use the most as we go forward, and as we do most of our calculations will be dealing with relative frequency probability. And it's an experiment. It's calculated, the relative frequency is calculated from the number of times an event happens divided by the total number of trials in the experiment. So we look at the probability of an event happening as the frequency, the number of times that it did happen, divided by however many times we did the experiment. Quite often what we're doing in an experiment is we're taking a survey. So the sample size down there would actually look at the number of surveys that we had. Now, for relative frequency probability, it's important that you know that we're looking at sampling. We're not looking at all possible outcomes. We don't have, if you want to say it this way, we don't have really population data. We just have a sample of our data that we're dealing with. Let's look at this example. 25 out of 1,000 randomly selected parts that are manufactured at a factory are found to be defective. Now, we assume that the defective parts are manufactured randomly. In other words, no one machine is malfunctioning that's making a bunch of parts defective. So this is random defection. What is the probability that the next part put out by this factory is defective? This would be a classic case of relative frequency probability because we took a sample, didn't we? We took a sample of parts, and then we counted the number of defective parts. So our sample size was 1,000. There were 1,000 parts that were examined, and 25 were found to be defective. So the probability that the next part or any part manufactured really by this company would be defective would be that frequency that was defective, which is 25, divided by the sample size, the number that we counted, and that was 1,000. So if we look at it, we have 0.025 is the probability of getting a defective part. Now I want you to look at this little frequency chart sort of that I put down here at the bottom and sort of see when we took the sample of 1,000 parts, we found that 25 were defective. That meant that 975 were not. They were good. So what the relative frequency or the probability, if you will, of a defective part is 0.025. The probability of a good part is 0.975. Now those two do add up because they're the only possibilities is it's either a good or defective part. They add up to the number 1, don't they? Looking at this, it looks like it's a pretty good probability, pretty good chances that we're going to get a good part from this company when we have the next one produced. Now we have a very important law or concept that I want you to understand. It's called the law of large numbers. This states that as the number of trials in a probability experiment increases, the difference between the theoretical probability of an event and the relative frequency probability approaches 0. Now the theoretical probability and the relative frequency in this case would get closer and closer together. Take, for example, the experiment of tossing a coin. Now, if we only tossed a coin a few times, you could understand how I might toss a coin 4 times and only get 1 heads out of it. Now, you know that's not the probability of getting heads. That looks like the probability of getting heads is only 0.25 or 1/4, 25%. And we know that's not the theoretical, the actual probability of tossing a coin and getting heads. So what happens as we keep tossing the coin? Well, if you toss it, for example, 100 times, you might get 64 heads. That's pretty realistic. That's looking like the probability of getting heads might be 64. It's definitely closer to our 50-50 that we know is true. But as we toss the coin more and more times, what you'll see is that relative frequency probability is going to get closer and closer to the actual probability of tossing a coin. The third conceptual approach to probability that you are responsible for is subjective probability. Now, this is a type that is really interesting. It's not going to be one that we do a lot of mathematical problems with because it doesn't lend itself to any mathematical formulas. Subjective probability is a type that is derived from an individual's personal judgment or from their own experience. And it tells you that this person knows a lot about probably their business and what specific outcome is likely to occur, but there are no formal calculations. The only thing that is reflected is the subject's opinions and their past experience. An example of this would be, and this is commonly happens, is a president of a company might have a hunch. He might think that, there's a 0.8 probability, an 80% chance that we would be successful if we tried this new brand of ice cream or this new brand of blue jeans or whatever. In this case, classical relative frequency, subjective, classical doesn't work, relative frequency doesn't work. This is the only thing that can be is subjective probability. He had a hunch. He came up with that number based on his past experience and his own judgment. You are probably familiar with some subjective probability cases of your own. Take a minute on page 4 and write your own probability example and explain why it's not a case of classical or relative frequency probability. One of my favorite examples of subjective probability is probably the Unicorn Frappuccino that came out in April of 2017 that Starbucks put out. I don't know if you remember it, but it created quite a craze. It was only out for 2 weeks, and it was pink and blue and sweet and sour, and it had some sparkly things that I think crunched or fizzed or something. But it was quite the phenomenon. In fact, people went in and bought this drink in such numbers that Starbucks was constantly running out of them. I've talked to many baristas who worked at that time, and they said, yeah, I couldn't even get one myself because we couldn't keep the stuff in stock. What you saw happen during that 2-week craze of the unicorn frappuccino was that the social media of that day was overwhelmed. I mean, it came really close to slowing down the internet, which is considered breaking the internet. What was happening, though, was people were going in, buying the frappuccino, taking a picture of themselves with it, and posting it, uploading it to their social media, whatever they wanted to, saying, I got my unicorn frappuccino. And this was quite an experiment for Starbucks, but it was an interesting one because I read several people who tried it who didn't really like it, but they still bought the drink just because it was such a item at that time. Now, what I really wanted to say is this: the person who decided to do a unicorn frappuccino didn't do any sort of marketing campaign. He didn't go out and do a survey and let people test this drink and see if it was going to work or not. They simply put together a drink that they knew the American people would go for, and it worked. But it was a prime example of what we call subjective probability, because the numbers didn't really back it up. Let's keep going with our definitions and our terminology. And as you can tell, this chapter is just, the terminology is going to be very, very important to you. So you really want to focus in, maybe make flashcards, make sure you understand all of these definitions. One is marginal probability. Now, marginal probability is a probability that an event will happen irrespective of any other event. It only considers that one event. Conditional probability is sort of the opposite. It's the probability of one event occurring in the presence of a second event. In other words, something else has to happen, and this has to happen in conjunction with it. That's what we call conditional probability. We have something called a contingency table, which is really a frequency table, and it displays two observations that are gathered at one time from members. This is quite frequently done as we will take something like, maybe we're looking at age, and we'll look at age, and at the same time we'll look at gender. And quite often that's one of the things that we do. It's done in marketing campaigns because men and women have a tendency to purchase and have different observations or different desires when purchasing materials, and so gender quite often does make a difference. Cells are considered the boxes that are inside this contingency table. Now, these cells, we would say, contain the numerical values for both observations, and then the margins are really the last column and the bottom row with the information in it. And they really regard, this is where we only find information about one type of observation. That's why it goes back to marginal probability. And I'll show you what we mean. Now, this is my example, or here's an example for you of a contingency table that had 100 students were surveyed, and they're taking a class. They're asked whether they're in favor or against online homework. And this table is really what we call a two-way classification of the responses of these 100 students. Now, what information have we captured? Why do we call it two-way? Well, first of all, we captured their opinion. Are they in favor or against? And then we captured gender, because quite often opinion changes based on gender. So we got male and female here. So we found that 45 males are in favor and 15 are against, for a total of 60 males, right? 36 females were in favor, 4 were against, for a total of 40. And then you can see the totals at the bottom and at the far right. Now, those total columns, total column and the total row, are really the margins of the table. And when we look at those numbers, it only represents one thing. In other words, 60 is how many total males there were in the survey. It doesn't answer whether these were in favor or against. It just says this is the total males. 81 represents the total that were in favor. It doesn't say whether they're male or female. 81 just represents that one condition, in favor. But if I go inside the table into the number 36, for example, well, that tells me two things about that number. Those are both in favor and female. Those are conditional numbers, aren't they? In favor is conditional, that 36 is conditional on the fact that they're female, or female there was conditional on the fact that they were in favor. It can work either one or two ways, and we'll work problems both of these ways in just a moment. So let's talk about these probabilities. The probability of male is 60 out of the total 100, which would be 0.6 or 60%. The probability of female is 40 out of 100, which would be 40%. Now what that means is if I was to randomly select one person out of this group of 100 students that were surveyed, there's a 40% probability that it would be a female, 60% probability that it would be male. Those are marginal probabilities. That's all they are. They're only considering one condition. The probability that this person that I select is in favor would be 81%, or 81 out of the 100, and the probability that they're against is 19 out of 100, 19%. This is marginal probability. All you can tell, the numbers I'm working with are in the margins. I didn't use those 4 inner cells at all. This is also called simple probability, and it only considers one of the variables from the group. So that's why we're only using either the last row or the last column to calculate our probabilities. Conditional probability is different. Conditional probability considers 2 of the variables from the table. We want the probability this time that an event will occur given that another event has already occurred. Now, when I say the event has already occurred, it means really given that I've already made a decision that this is the condition I'm interested in. So if A and B are 2 separate events, we would say the conditional probability of A given B, the probability of A given that B has already happened, is written as probability of A, and that's just a straight line, is how we say given B. That's how we read it, probability of A given B. The most important thing for you to remember when you're dealing with conditional probability, when you're dealing with a given condition, is it restricts your view of the table to the given condition. So if I have the probability of in favor given male, what I'm saying is I want to know what the probability of in favor is only considering the males in this table, okay? So what do? I restrict my view of the table to the male, and this time it's a row. It could be a column, but this time male is really a row. So let's don't even look at the rest of it. You can circle it if you want to. Circle the given condition, and this time it was just that one row of male. So I'm putting the number that are in favor. Well, the only number I have in favor to look at this time is the males in favor, and that would be what I'm looking for, which is 45 over the total number. This time it is the total number of males, not the total number of people surveyed in my table. Now use the same procedure that I just did, and I want you to calculate the probability of a student being selected that is female, given that this student is in favor of online homework. First, write it out. Probability of female given in favor. You should be able to write that probability statement just like I did in favor male before. I said female given in favor, right? So here's what it should look like. Probability of female given in favor, and you should be writing your probability statements just like this with the words, because that'll help you later on. Straight line says given. Probability of female given in favor means that the in favor condition, the in favor part of the table is all I want to look at. Well, in favor happened to be a column, so I take out everything else in my table. I'm only going to look at the in favor column. And then I look at the number of females in that in favor column, and I put it over the total number in the in favor column, and I come up with 36 over 81, or 0.44, or 44%. Now let's move on to another concept and start talking about something called compound events. Now, we need to define mutually exclusive and mutually non-exclusive events. Mutually exclusive events cannot occur together. They can't happen together. If you look at a couple of courses here at the college that you cannot take during the same semester, you might say, well, MAT 1030, MAT 1100, MAC, which is college algebra 1105, you can't take those together. They won't allow you to take them in the same semester, so those are mutually exclusive events. You're either taking one or the other, but you're not taking both. Now, mutually non-exclusive events can happen together. You can take for example, college algebra and statistics at the same time is a really bad idea, but you can do it, okay? So these events are called mutually non-exclusive because they can happen together. Now, why are we focusing on these terms is because some of your formulas are going to depend on mutually exclusive and mutually non-exclusive events, and you're going to want to recognize what type of events you're dealing with. Now, just like mutually exclusive and mutually non-exclusive are important to know, whether an event is independent of another event is important to note because it will affect your formulas later on. So here's your definition for independence. Two events are said to be independent if the occurrence of one does not affect the probability of the occurrence of the other one. In other words, A and B would be independent events if the fact that one happened or occurred doesn't affect the probability or the chance that the other would happen. We write this out as a probability statement, as we say the probability of A given that B happens is equal to the probability of A, or we could reverse those letters and say the probability of B given that A happens is equal to the probability of B. This is what we call the check for independence. Let's go back to our students and the question that they were asked about online homework. Let's look and see if the events in favor and female are independent. Now, what is that asking? Well, it's really asking the question, did males and females answer this question about being in favor of online homework differently? In other words, I'm going to look at the events female and in favor, and I'm going to see if they are dependent on each other, if they changed based on, if in favor, the answer in favor changed based on whether it was female or male that answered the question. So remember our check for independence. We look to see if the probability of A is equal to the probability of A given B. Now, that's in your formula sheet. It's important that you do get those events in the right order. It has to be the probability of a certain event is equal to the probability of that same event given that the other event has happened. So that is important. And it won't be the same for all probabilities. Later on, that formula is going to change on you for other things. So pay attention to the order, okay? So first we look at the marginal probability of in favor. What's the probability that in favor happened? Well, it's a marginal. It only deals with those numbers in the margins. 81 out of 100 were in favor, and that's 0.81. Then we look at the conditional probability of somebody being in favor given that they were female. Now this time we only look at the in favor condition of female. So it's only that middle row that we're looking at. So we're looking at the number of females in favor. That's 36 out of the total of females, and that's 40. So 36 out of 40 is 0.9. Now we would say, are those two probabilities equal to each other? They're not. They're not even close to each other. So that means the two events are dependent on each other. If the test for independence fails, in other words, if they're not equal to each other, then they are not independent. They are dependent on each other. It did make a difference whether the person who answered the survey was male or female in answering the question, were they in favor of online homework? Now let's do an exercise. It's going to be like some of your homework problems. And in a survey, I've given you 300 randomly selected adults who drive or asked whether they usually drive a car or a truck. And of the 300, I've got some numbers that I'm giving you, some specific numbers to be filled in. But notice that I'm asking you to make a two-way contingency table. And you could have filled in these headings, or you can. You've got a blank at the bottom of page 8. You can fill in these headings any way you really want to. But I've put truck and car, and then total, and then men, women, and total. Truck and car across the top, men, women on the side. It could have been done in the reverse of that, but you might want to stay with me just for this example so that my example makes more sense to you. Now look at my numbers. Of the 300 adults, 140 are men and 105 drive a truck. Of the 140 men, 65 drive a truck. And it wants to know, are the events driving a truck and man independent of each other? So what we have to do first is take these four numbers that we've been given, fill in our contingency table, and then figure out what the other numbers are. And it's not as hard as you might think. I start with my totals, and then I look at the numbers I've been given, and it says in a survey, 300 randomly selected adults. That is my total that I've been given. That's the total of everything. And then it says, of the 300 adults, 140 are men, comma. So that's complete thought by itself. 140 men. Where's the total men? It would be over here. And 105 drive a truck, period. Another complete thought all by itself. So that's the total that drive a truck. Where's that number? Over here. And then it says, of the 140 men. So I know I'm working on this row right here. Of the 140 men, 65 drive a truck. So it's got to fill in one of these inner cells, doesn't it? Now once I have this done, I can fill in the rest of the numbers. Go ahead and take a minute and do that. Well, as you've probably already seen, you would say 140 minus 65. That's going to give me 75. And I can do these two. I can say 105 minus the 65. That's going to leave me 40 women. I have these two numbers to deal with. I could say 300 minus 140. I end up with 160. And here I can get this number by saying 300 minus 105, and I come up with 195. And next, let's see what I've got next. The last one I've got several ways to get it. But what if I say 160 minus 40, and it's 120 now? And go through here and check it. 75, 120, 195. And these look like they're adding up correctly, and I've got my contingency table filled in correctly. So let's finish the problem. We want to know if driving a truck, we'll call that event A, and man, and we'll call that event B, is independent. What we're really saying is the probability of A equal to the probability of A given that B has already happened. In other words, we've already made the decision that B is a given in this condition. Okay, so I'm going to say, what's the probability of A? That's the probability of truck, isn't it? The probability of truck would be, okay, total trucks here. I've got 105, don't I? Divided by 300. And then the probability of A given B, well, that's going to be the probability of truck given man. Okay, so I can only look at the given condition. I'm only going to be able to look at the men. I'm only going to be able to look at this one row. I'll underline it so I don't get confused. And I say, how many trucks are there? Well, there's 65. What's my total? Well, it's 140. And I want to know, is 105 over 300 equal to 65 over 140? And I'm going to put a question mark over that equal because I don't know if they're equal or not. Well, I do the math, and I find that 105 divided by 300 is 0.35. That's the probability of driving a truck. And the probability of driving a truck, given that it's only considering the men, is 65 over 105, and that's 0.6195. These are not equal. Therefore, the events driving a man and truck are not independent. They are dependent on each other. Now, you have an on-your-own activity to do on page 9. And I want you to note that I've given you a table that's people who haven't shopped and have never shopped on the internet, and I have not put the total row or the total column. Your first job is always going to be to put the totals in. So you may have to do some math here. But you want a total row, total column. Your total is going to be the number of randomly selected adults. And I think that number should equal 2,000 when you get down there. So figure that one out. And then it asks some questions. Are the events male and female mutually exclusive? Now look, mutually exclusive is not a mathematical check. Mutually exclusive says, can I find somebody in this table who is both male and female? I mean, well, the males are up here and the females are down here. So in this table, it doesn't exist that somebody said that answered the question that they were both male and female. So mutually exclusive, yes, they do not happen together. What about the events shopped and male? Ask yourself the question, can you find somebody who both has shopped the internet and is male? If you have that number, then they are mutually non-exclusive or not mutually exclusive. You need to write that down and your explanation there. The next test I've asked you to do is the test for independence. This is a mathematical check. You're going to have to say, is the probability of A equal to the probability of A given B? Make one of the conditions A and the other condition B. It doesn't matter which one. And do the mathematical check for independence. Now, another definition, and when we're talking about two events and how they affect each other, is complements of events. If we have the complement of an event we'll define as A, we would say that's A complement, which we call A bar or A complement. We put a bar over the A. And that event, A complement, is the event that includes every outcome that is not in the event A. Okay, everything that's not in A would be an A complement. So if we added A and A complement together, we would always get a probability of 1 because these events are complementary events. In other words, what that means is they will always sum up to equal 1. They include all possibilities. For example, if you were to select, if your event was to select a blue car from a set of cars, the complement of selecting a blue car would be to select a car that is not blue. So what are the possibilities? Well, either a blue car or a not blue car. When I add up the probabilities for those, they would always equal the number 1. They are complementary events. Here's another example for you. There's a group of 1,000 adults. 600 have been married at least one time. And one adult's randomly selected from the group. And I want to know what the two complementary events are for the experiment and what are the probabilities of these two complementary events happening. So we have to first define the events. We'll call event A that the selected adult has been married at least once. So A complement, the selected adult has not been married at least once or has never been married. So the probabilities of those would be going back to the numbers that we surveyed. In a group of 1,000 adults, 600 have been married at least once. That's a probability. In other words, out of the 1,600 are in event A, they have been married at least once. So 60%, 0.6 or 60% have been married at least once. What's a complement? Well, I can say the others. How many were left that had been never married? Well, 400 out of the 1,000 are 0.4, but if you look at 0.6 and 0.4, you can see they add up to equal the number 1. So we didn't really have to do that 400 divided by 1,000 for the complementary event. We just had to know that that event plus our other event, the complementary events, we're going to add up to equal the number 1. Now let's take another example using that truck and car drivers, okay? We have 300 adults total, and we know that 105 of them drive trucks. And we know that we're going to select one adult randomly, and we want to let A be the event that this adult drives a truck. So event A is going to be drives a truck. You can go ahead and define that at the bottom of page 10. A is equal to driving a truck. Okay, so what's the complement of A? If A is driving a truck, what's A complement? Well, it's going to be either driving a car or not driving a truck. Well, the only other choice for driving a truck that we've got here is driving a car. So you can put not driving a truck or you can put driving a car for the definition for A complement. Now I want you to find the numbers that represent the probabilities for A and the probability for A complement. In other words, what's the probability that I would select one adult from this group of 300 and that adult would drive a truck? Look at the total, because this is a marginal probability, right? It's only considering one thing, whether they drive a truck or car. So let's look at the margins. 105 divided by 300 are the numbers I'm interested in. That's my probability for driving a truck. Now, from that, you don't even need the chart anymore. You can calculate the complement, which is the complementary event, which is driving a car, just because you know the probability of A, driving a truck. So what numbers did you get? You should have said 105 divided by 300, 0.35 is what I got. And then I could have just looked at, I could have done the other math with the numbers in the table. Not driving a truck is really representing car there. But I could have also said 1 minus 0.35 and come up with 0.65 for the complementary event. Now you've got another on your own activity on page 11, and this one is very important. It has quite a few numbers, but to make the math a little easier, I'm going to go ahead and tell you that the totals, now you do need, for this contingency table, you're going to have a total column up here, and you're going to have a total row here. But if you'll look inside the narration, the numbers have been added for you. So you should be able to see, for example, what's the total number of chocolate, and it says 2,049 answered chocolate. And so you don't really have to do too much math, just read carefully and you should be able to get those. Then I want you to go and answer the questions and see how well you understand the material that you've just covered. The probability that a person would be female, responded chips given. There's your given condition. And then you want to know, I want to know if they're mutually exclusive. Some events are mutually exclusive. And then I want you to do the test for independence. So basically on this page, you get to test yourself on everything we have covered. So this is a very important page for you to test your comprehension. Now next I want to talk about something called joint events, and I call those AND events. They're also called intersection events. Now when you put this on a flashcard, you need to say that. AND events, joint events, intersection events all mean the same thing. So what we're talking about is A and B being two separate events that are defined, and this is my sample space representation with a Venn diagram. And the AND event of A and B is all of the events that are common to both A and to B. That makes sense, doesn't it? We also use this symbol, looks like an upside down U, to say A and B. So it would be the probability, when you're looking at it, the probability of it being in event A and in event B. So A and B really represents the set of values that make both statements true, if you want to think of it that way. It's the compound statement is true. It's the overlapping of the two sets. So I've got a contingency table that I've got here that we can work with and use as an example. And this one is looking for probability of a person being in event A and B. And there's what we call the multiplication rule. The probability of A and B, both of them happening together, is a multiplication. We multiply the probability of A times the probability of B. That's how we get the probability of A and B. So we just multiply the probabilities together, and we should get the AND probability, the joint or the intersection probability. Now, think about it with this table. I've got, what's the probability that I select one person from this group of 500, and that person is both male and likes coffee, drinks coffee? Well, what's the probability of male? The probability of male is a marginal probability, isn't it? 240 over 500. And what's the probability that somebody likes coffee? Another marginal probability, which is 325 over 500. So I take those two and multiply them together, and I would come up with the number 0.312 or 31.2%. But I want you to notice something. When I look at male and coffee, I realize these are not mutually exclusive. I can find a number in my contingency table that is both male and likes coffee. Well, there's 156 of them. This time, if I write it over the total down there of 500, I'll get the same number, the same percentage. It's a shortcut, if you will. It's a shortcut to the multiplication rule. If you have a contingency table, you can simply look it up. You'll be looking at one of the inner cells, and you'll be putting it over the total in the margin, okay? So we'll be looking at a number that's inside in one of our four inner cells of our table, and we'll be putting it always over the total, but that will give us the same numbers, the same probability. So use the shortcut when you have a contingency table. Now remember, this is the multiplication rule for independent events. Now I told you it was going to matter if your events were dependent or independent later on. This multiplication rule in this formula is simply for independent events. Simple probability, the probability of A times the probability of B, is only if the events are not dependent on each other. Now let's look at something that doesn't have a contingency table associated with it. Let's take this example. And we have a street corner, for example. It has two red lights there. And the probability is 0.03 that any red light of this type would fail. Now we want to know the probability that both of these red lights are going to fail at the same time. So we want to know the probability that first red light 1 will fail and red light 2 will fail. That's saying at the same time. So this is going to be a joint probability, isn't it? Now you ask yourself the other question, are the events independent? Well, one red light failing should not ever affect whether the other red light fails or not. It shouldn't, unless it's an issue other than the red light failing itself. So yeah, they would be independent events, and that's just a common sense check for independence. Sometimes we don't have to do the numerical, we don't have the numbers to do the numerical check, but obviously this is an equipment question, and whether a red light fails doesn't affect any other red light failing or not. So these are going to be independent events, and we would simply find those probabilities and multiply them together. So what does it look like? Well, first we define the events. Event A, we'll say, is that red light 1 fails, and event B is that red light 2 fails, and then look at what the probability of them failing is. Well, the probability of any red light failing is 0.03, so I could write that down for both of them. Then I go and take my formula and I say the probability of A and B happening is the probability of A times the probability of B, or 0.03 times 0.03, which gives me 0.0009. Now you think about it, usually when you multiply numbers together, they get bigger, right? Except these are fractions, decimals. When you multiply fractions or decimals together, the result is smaller. And you would expect joint probability, the probability that both things would happen, to be smaller than the probability that either one would happen independently. So what if? What if these are not independent events that we're talking about? What if two events are dependent on each other and we're asked to find joint or and probability? Well, we have another formula for that. The probability of A and B, if the events are dependent, is equal to the probability of B. Now notice that's the second event. The second event times the probability of the first event, A, given that B has already happened. It's very important that these are in the correct order when you write your probability statements, okay? I'll give you an example. A high school has 200 seniors and 140 of them will be going to college next year. I've put the number on your chart for you. 40 are going directly to work. The remainder are taking a year off. 50 of them are going to college to play sports, and 30 of them are going directly to work. 30 that are going directly to work play sports. So those are the ones that play sports. And 5 of the seniors taking a gap year play sports, and I put all those numbers in so that you can take those numbers that I've added to your chart and you can figure out the rest of the contingency table. The question you're going to answer once you've done this is, what's the probability that a senior is taking a gap year? What's the probability that a senior who plays sports is taking a gap year? So this is where you stop your tape and you try to work the problem on your own so that you'll have a good idea of what you know and what you don't know before you continue. So I filled in the table, as you should have done by now, and I'm going to ask the questions, or answer the questions. What's the probability that a senior is taking a gap year? Now all of these are seniors, okay? But what we're really asking is, what's the probability of a gap year, right? Okay, so the probability of a gap year is how many people in this survey are having a gap year. Well, there's 200 out of the 200. There's 20 out of the 200. So I'm going to write it like this: probability of gap is equal to, well, here's the gaps, 20 out of 200, and that's going to be 0.1. So that answers my question about that probability, which is a marginal probability. It's not really complicated. And then I want to know the probability that a senior who plays sports is taking a gap year. So what we're saying is play sports and gap year, right? What's the probability of sports and gap year? Okay, so the probability of sports and gap year, and I could say, okay, this is event A and this is event B, I can identify them, has to equal the probability of that second event, which we would call event B, which I'm going to call gap, right? And I'm going back to my formula, times the probability of, this time it's A given that B has already happened, so it's going to say A, which is sports, given that gap has already happened. Well, let's look at these like they're fractions, okay? What's the probability of a gap here? Well, that would be 20 out of the 200. And I want to multiply that times the probability of sports given the gap here has already happened. I'm only going to be looking at these numbers here this time, this one row, this gap here, and sports would be 5 over the 20. Now, if I'm multiplying fractions and I have a numerator and a denominator the same, really they cancel, don't they? So what do I have? I have 5 over 200, don't I? Which is really equal to 0.025, but that's not really, I mean, that tells me what that probability is. But look what happened, everybody. I had 5 over 200. Go back up here and tell me, what's your sports and gap year number here? Well, here it is. Sports and gap year is here, 5 over 200. So my shortcut also works that I use with independent events. It also works with dependent events. So your shortcut will work for you if you have a contingency table. You can just look up the number that joins both of the events together, put it over the total, and you'll still get the right answer. Now, another thing about conditional probability you may be given is the probability of an individual outcome, and then you may be given a joint probability of that particular outcome in another one. If you're given just numbers and not a contingency table, how do you find your answers? Well, the probability that both events will occur, assuming that these are dependent events, is calculated like this. We say the probability of A, given that B happens, is equal to the probability of A and B divided by, this time, the probability of B. I want to give you an example of that. So if we know the probability that a selected student is going to be a freshman is 0.4, and then we know the joint probability that the student is a nursing student and a freshman is 0.02, then we want the conditional probability that the student selected at random is a nursing student given the student is a freshman. Now this is joint probability, has to be both a nursing student and a freshman, and these events are dependent on each other. Most of the time you'll be told if events are independent or dependent, okay? So from this information we can say the probability of freshman is equal to 0.4, and the probability of freshman and nursing student is 0.02. So you write down everything you know first, and we know also that the probability of a nursing student given freshman is going to be equal to the division. We'll take that joint probability, the and probability, and divide it by the individual probability, and we'll come up with the given, the conditional probability. Now let's talk about something that's really kind of common sense, but it's something that you do need to consider, and it's joint or and probability of mutually exclusive events. Well, mutually exclusive events simply cannot happen together. That's the definition. So, for example, you can't be present sitting in the classroom and not in the classroom at the same time. Joint probability means that these events do happen together. They're and events, right? So what happens if what happens to the probability that mutually exclusive events happen together? Well, you're asking what's the probability that events that cannot happen together do happen together, and there's no chance of that. There is a 0 probability for mutually exclusive events happening together. So the joint probability of mutually exclusive events is always 0. So here's some examples of mutually exclusive events. One would be tossing a coin and getting an answer that was both heads and tails on one toss of a coin. Simply doesn't happen. To take a turn at an intersection and turn left and right at the same time. To fail and pass the same test. To be standing in Florida and New York State at the same time. Now these are mutually exclusive events. They simply don't happen together. I want you to write down your own mutually exclusive event on page 14. And then I have an on your own activity I want you to complete. Now this activity is using the same table that we were working with before, so you might want to fill in that the totals column and the total row at the bottom and the side of it, and then answer the questions at the bottom. You've got one person is randomly selected. You want the probability of the intersection, the and probability of the events female and ice cream, and you want the probability of the intersection of the events male and pizza. You should be able to use your contingency table to look up those probabilities. The next set of formulas we're going to look at, and the next type of combination of events, is called the union, and we call that the OR set of events, and it has what we call an addition rule that goes with that. Remember, we did joint and probability, and we had the multiplication rule. When we do union of events, we do the addition rule. So, what is the definition? An outcome is the event A, or of the event A or B happening, is the outcome that is in A or is in B. So it can be in either one, or it can even be in both, and it would count for part of our event. That's why we have an addition rule. We add the two together. Now, the probability of the union of two mutually exclusive events, if they happen separately from each other, then we simply add them. There's no overlapping probabilities to consider. But if the two events that we're talking about are not mutually exclusive, they're mutually non-exclusive, then what's going to happen is we're going to, in adding A and B, we're going to have some events that are in both A and B. Well, we would have added them in twice when we added the probability of A and probability of B. So we'll have to take that overlapping section and subtract it. And that's going to be an interesting formula for you to work with. So here's a table for you to work with. It was 500 students taking statistics at IRSC, and they were asked if they work, either full-time, part-time, or no work. And then they were also asked, do they belong to a club? And that's their two-part contingency table. And we're interested in the union, the OR events, work full-time and no work. Okay, now I know there's a word and in between those, but you've just been told that it's a union. In other words, what it is we want the union, or we want the probability of working full-time or no work. So you kind of have to read your statements carefully. They may use the word and just to tell you the two different events, okay? So I write it down. I say the probability of A or B, are they mutually exclusive? I got to know which formula to use. So I look at them, working full-time and no work. Yep, there's nobody up there who has answered that they both work full-time and don't work at all, right? So these are mutually exclusive events. All I have to do is find their probabilities and add them together. So it's going to be the probability of A plus B. In other words, the probability of full-time plus the probability of no work. And that's going to be some marginal probabilities, actually. Probability of full-time, 110 students over the 500, plus the probability of no work at all. Well, there's 220 of those out of the 500. And then I'm adding fractions with common denominators. Now, embrace fractions. Don't go ahead and do decimals or change everything to decimals right away, because it makes your math more confusing than using the fractions at first. Now, I'm adding fractions with the same denominator, so I simply add the denominators, and then I do my final division, and I come up with 0.66 or 66%. Now let's take another example. Let's use the same chart and say, I want to describe the union of the events, and this is just the two events, work full-time and club. So I'm saying, what's the probability of somebody working full-time or being in a club? Well, you ask yourself the mutually exclusive question. Can somebody work full-time and be in a club? And they can, because I've got people right here that work full-time that are also in a club, don't I? So I'm going to have some overlaps that I'm going to have to subtract. I'm going to have to use my non-exclusive formula, probability of A plus probability of B minus the probability of both of them happening together. So how does that look when I write it in words? Probability of full-time or club is equal to the probability of full-time plus the probability of club minus the probability of both of them happening together, the joint or and probability of full-time and club. So what do I find? Well, I can look these numbers up pretty easy. Probability of full-time, there's 110 over the 500. Probability of club, well, there's 200 over the 500. And probability of both happening together. Well, where are my full-time people that are also in a club? Full-time clubs are right here. What number do I put it over? Also the 500. Look, all the denominators are the same. I just do the math with the numerators. I say 110 plus 200 minus 60. And I end up with 250 over 500, 0.5 or 50%. Now look, this will always happen this way when you're doing it. If you do the numbers correctly, you'll always have the same denominator. So you just do the math with the numerators and do the division at the end. Now on page 16, you have another chart, another contingency chart with a narration for you to fill in the numbers. You've got a group of 2,500 persons. 1,400 of those are right-handed, 600 have green eyes, 400 are right-handed and have green eyes. So you've basically been given 4 numbers and you should be able to fill in the chart from that. Once that's done, you want to find the probability that one person selected at random from this group would be left-handed or have green eyes. Now, is this mutually exclusive? Ask yourself that question, and then you'll know which formula to use. Be sure you try this completely using the previous pages that we worked before you look at your answer or continue the tape. Go ahead and check and see if you've filled in your table correctly. You should have 200 left-hand, or 200 that are green eyes left-handed, and 600 total green eyes, 1,900 that are not green eyes, and I think I've got the numbers correct on this chart before you go forward. So let's finish our problem. Now, if we use the addition rule, we notice that they are not mutually exclusive. People could be left-handed and have green eyes together. So we're going to say the probability of left-handed plus the probability of green eyes minus the probability of left-handed and green eyes. In other words, when I add the number that are left-handed, these 1,100, and I add the number that have green eyes, these 600, I have included this group twice, okay? They were included in that 1,100. They were also included in that 600. They'll have to be subtracted out once. I put all of these numbers over the total, which is 2,500. I do all my math. I say 1,100 plus 600 minus 200 and put that 1,500 over 2,500, and then I do the division and come up with the answer, which is 0.6 or 60%. Now on the bottom of page 16, I've got an on your own activity. I've got another contingency table that I've started for you, but I haven't finished. I want you to know that this is one column, less than 30 minutes late, then there's another one, 30 to an hour late, and then more than 1 hour late. So over here, I would come in and write a total column, and down here, I would come and write a total row. And be sure you do those numbers before you answer the questions at the bottom. I want you to note something about question C. There is no math required in question C. See if you can figure out why. There's an entire section of mathematics called combinatorics, which is really counting things. Now, we have some basic simple rules to counting, and if you want to find total outcomes, what you would do is find the steps, each of the possibilities in each step, and multiply those together. So if you have an experiment and it has 3 steps or 3 stages to it, it'll have 3 different sets of outcomes. This first step would have, let's see, A outcomes, and the second step has B outcomes, and the third has C outcomes. Well, what are the total possibilities, total number of outcomes for this experiment? Well, we would simply multiply the number of outcomes in the first step, the second step, and the third step together. So, for example, let's talk about tossing a coin. If we tossed a coin 3 times, how many total outcomes does the experiment have? Now remember, we did this earlier. We drew a tree diagram and we said, okay, there's 2 possibilities, and then based on that, there's 2 possibilities for the next step, and then for the third toss, there would be 2 possibilities. So how would you get this without drawing a tree diagram? Well, you would say, you would count each toss of a coin as one step of the experiment. So possible outcomes for the first step would be 2. Possible outcomes for the second step would be 2, and possible outcomes for the third step would be 2. When we multiply the 2's together, we get 8 possibilities for tossing the coin. If you go back and look at our tree diagram that we drew, you'll see that this is very consistent with the 8 possibilities we came up with. Let's see if you can figure this one out. What I'm going to ask you to consider is buying a house. Now, you can choose, you make two decisions when you're buying a house. In the financing part of it, you choose between a fixed and a variable interest rate, and then you choose your payment period. You have choices. You have a fixed or variable rate is your first choice, and your second choice would be payment period of either 15, 20, or 30 years. How many total possible outcomes are there in those two decisions? Think about the two decisions as steps. The first step, I'm going to choose either variable or fixed rate. The second step, I'm going to choose the payment period. And I've got three different choices. So how many possible outcomes would I have in this decision-making process of buying a house? Well, it's very simple. In step one, I have two possibilities or two possible outcomes. In step two, I have three possibilities or three possible outcomes. I would take those possible outcomes, multiply them together, and come up with 2 times 3 or 6 final outcomes. When we talk about counting things, we need to get some math or go back and refresh some math or some algebra that you've already had. And one thing we need to consider is, what is a factorial? Because that's going to be in your formulas coming up. We represent a factorial as n, the number, with an exclamation after it, and we call that n factorial. And it's really the product of all of the integers from whatever that number is all the way down to 1. In other words, if I had 2 factorial, it would be 2 times 1. If I had 3 factorial, it would be 3 times 2 times 1. So we have to get another definition out of the way first, though, is 0 factorial. What is that? Well, by definition, just memorize it, 0 factorial is always equal to the number 1. So let's complete page 18 and see if you can get these factorials correct. First, look at 6 factorial. What is it? 6 times 5 times 4 times 3 times 2 times 1. Try it. You should get 720. And then evaluate the same way 9 factorial. And then I want you to look at 8 minus 2 factorial. Now, remember, do the math inside the parentheses first, and then complete the factorial. And finally, evaluate 3 minus 3 factorial. So the math behind factorials is really fairly simple, and I've gone ahead and completed these for you. Of course, 6 factorial ended up being in there twice, and I didn't rewrite it for you, and 0 factorial is always equal to the number 1. But I do want to show you, and you should have a way to do this on any calculator you're using, especially on your graphing calculators. So let's take a really quick look at this graphing calculator. I hope you can see it. I'll tell you what I'm doing as I go. And watch how we can do factorials. First, we're going to enter the number that we want the factorial of, and I'm going to do 9 here. I want 9 factorial, so I'll enter the number 9. And then I have to go to my math button. I say math, and I go over here to the probability menu, and once on the probability menu, I can select a number 4 for the factorial, or I can arrow down, whatever I want to do, and select that, and it puts in 9 factorial, and then I just hit enter, and it gives me my answer. So find out how to do factorials on your calculator. You're going to end up using that quite a bit. Another mathematical term and function we need to be familiar with is how to do combinations. Now, combinations really calculate the number of ways that we can select a certain number of items out of a certain number of items. And we say we're selecting X is the item we're being selected, N is our group that we're selecting it from, and we write it as N combination X. N is always the number we're selecting from. It's always going to be the bigger number. X is how many are we selecting in each group. Now, for combinations, order does not make a difference, and that's something that's going to be important for you to remember. You have a formula for combinations, and that formula is n factorial divided by x factorial times n minus x factorial. Now, this may look like a lot of math, but if you have your factorial button on your calculator, it's not too complicated, and you can always use it. I'm going to show you, it's really not too hard to do this even without the factorial button most of the time, but sometimes the numbers will get big enough that you'll need that button. For example, let's say we've got an ice cream counter that has 5 different flavors of ice cream, and we want to know how many different combinations of double scoop cones we can make. So how many flavors are we choosing from? That's going to be our N. So here it's 5. And how many are we selecting at a time? Well, a double scoop cone, we would be selecting 2 at a time. So we fill in our factorial combination by saying 5 factorial, which is n factorial, divided by x factorial, or 2 factorial, times 5 minus 2 factorial. And that's going to simplify down to 5 factorial divided by 2 factorial times 3 factorial. Now, you don't multiply factorials together, you simply write them out, and then you start canceling items in the numerator and denominator that are alike. And so what I really end up here with is these 3's, these 2's, these 1's cancel. I really end up with 20 divided by 2, and that's going to be, of course, 10 different combinations out of those 5 flavors of ice cream. Now, I want you to note that in this particular problem, it looks like all I did was say 5 times 2 to get 10. And that's not the case. You know how math sometimes just happens to work in your favor? This is one of those times if you made that mistake, it would work. Normally, it would not work for you. So let's try another example, this exercise at the bottom. 3 members of a committee are randomly selected from 5 people. And we want to know how many different combinations are possible. Well, how many are we selecting from? That's our group that we're selecting from, and I'm selecting 5 out of 5, and I'm selecting 3 at a time. Go ahead and fill this one in and see if you can come up with the correct combination. So hopefully you've had a chance to finish. Let's say I've got a combination. Out of 5, I'm selecting 3 at a time. Well, that means I'm going to be saying x factorial divided by n factorial divided by x factorial times n minus x factorial, filled in my formula. And now I've got 5 factorial divided by 3 factorial times 2 factorial. Well, that's the same formula that I had above, so you actually really don't even have to do the math on this one. I can tell exactly what's happened. But I do want to note one thing. If I have factorials like this, I could say, okay, the largest factorial in the denominator is 3 factorial. Let's just go down to 3 factorial and leave 3 factorial in the numerator. So I said 5 times 4 times 3 factorial. You can see how this would work with bigger numbers. And then in the denominator, I've got 3 factorial times 2 times 1. That's my lower, so that I cancel it out. And now I just have 20 divided by 2, 10, easy math. Let's take a look at your calculator and see once again how we can do combinations with your calculator, because it can do this for you. Now I'm once again going to the math button here, and I'm going over, if I can get this glare off your screen, I'm going over to probabilities, and you can see I've got NPR and NCR. Now pretend those R's are X's because it's really the same thing. Now this is a combination. This is a permutation, which we're going to talk about in a minute. So I'm going to select number 3 here because that's what I want to use. And my calculator gives me a couple of little blanks. I fill in N, which is, okay, 5. And then I come over and I fill in the X, which is 2. And I hit enter, and it gives me 10. Most of the time, if you don't have a TI-84, what you're going to be doing is putting the number 5, the N value first, then you're going to be going to math, combination, and then you're going to hit that button and enter. It'll let you enter the 2. It'll enter the 5 yourself, put the combination in and enter the 2. If it doesn't give you the little menu like mine, try that. If that's confusing for you, Google how to do combinations on whatever type of calculator you have, and it'll show you. So, what's the difference between a combination and a permutation? Well, a permutation tells us the total number of X, the way we can select X items out of N items, same thing, but in a permutation, order matters. The number of permutations seeking X elements from N elements is always used only when order has been told in the problem that it makes a difference. And here's our formula for permutations. It's listed, or it's itemized the same way. We start with the number of items we're selecting from, and then the number that we want selected at a time, and we say n factorial divided by n minus x factorial is that permutation. The only difference, note, is that we didn't have times x factorial out here at the beginning, right? So it's just a little difference in our permutation and combination formula. And here's an example. A padlock, it has 4 digits on it, and these digits go from 0 to 9. So how many different possibilities can you find to open this lock? Now, in a padlock, of course, order does make a difference because each digit has to be, specific to whatever you've set it to, right? So order of it does make a difference in this one. So I start with my permutation formula and I say, well, I've got 10 numbers. 0 to 9 is not 9 numbers, it's 10. 0 counts, right? So I've got 10 is my end value. And out of 10, I've got 10 minus 4 is the number of digits I've got here, 4 different choices that I want to make. And that comes out to be 10 factorial over 6 factorial. And when I look at it, it comes out to be 5,040 combinations. Now, so really, it's really permutations though, isn't it? Not combinations. We call it a combination lock, and perhaps we have misnamed it. It should probably be called a permutation lock. And once again, your graphing calculators can do permutations for you. Remember where we were? We were in math, right? And we looked over at the probabilities, and that's the probability menu, and I found number 2 was permutations. And mine allows me to enter the numbers for it, of course, and what were the numbers I was working with? I said 10, and then I said I want 4 selected at a time, and how many different combinations or permutations for my combination lock can I get? And there's my answer, 5,040. Once again, if you're not dealing with the type of calculator I am, you might have to enter this 10 first, then go math, probability, permutation, and then enter the X value or the number 4. Page 21 is an activity for you to complete on your own, dealing with combinations and permutations. It's important that you do know how to do these with your calculator or by hand because your next set of formulas is going to involve these items. I've given you some scenarios. How do you know if it's a permutation or a combination? Well, if order is mentioned at all in the problem, then it is a permutation, okay? If order is mentioned at all. If it just says, 2 are randomly selected, how many arrangements, well, that's no order is mentioned. But if it says something about, I had to select this one first or this one second, or anytime order is mentioned at all, it is a permutation. Now this concludes Chapter 3's lecture. After you finish all this work, you should be able to complete the homework and the quizzes and get ready for Chapter 4.